here today at my vegetable garden, or what's left of it. This is what happens when you don't water it for a week. You lose a lot of your plants. And we say vegetable garden, you say that loosely because tomatoes are actually fruit, not that it really matters. What we're doing today is we're gonna weigh my tomatoes, and I've been doing this all year. The reason why is this here I built, and it's expensive to build an above ground garden, but what I want to see is if I plant it in the soil, am I going to get the same results that I got this year? So I'm going to pick a few of these tomatoes, these cherry tomatoes, because they're my favorite, and we're going to go over and we're going to weigh them. Alright, so what I do is I'm taking my tomatoes. I had to zero out my scale, even though the wind is slightly affecting my scale here, and I'm going to weigh them. And I'm weighing them in grams. I know this one's going to be about 5 or 6. Actually, this one is 7, a little bigger than I thought. 7. So I go less than 7, less than 8, greater than 7, and I record it. And I do the same thing, and I've been doing this all summer. As I do these, let's see what this one is. Well, let's get a big one and see what the biggest one we have is. This one today, the biggest one we have. There it is there. It's less than 12, greater than 11. Okay, so if you want to see, come in here and you'll look at my chart that I created. My chart is 0 less than 1, 1 less than 2, and I just quickly record these every day. And the reason why is later on, I want to see if I plant this in the ground, am I going to get the same results? Are they going to be the same size? The yield is easy. I can just count how many there are and see if I get the same yield or not. But if I turn this thing this way, you'll notice a distinct pattern here. I mean, this is really, really crazy how close this is to perfectly symmetrical. And a lot of things occur this way in nature, and they call this the normal curve, and that's what we'll be talking about today. The only other question I have was what I did today and what I'm going to do next year. Is this an experiment or an observational study? I want you to think about that, and that's what we'll start with on our next video. Hello, welcome to the section on normal distributions and density curves. We've talked about the shape of a distribution, and you'll see this one here. This is symmetrical. It's perfectly symmetrical. Has one peak and then goes out the same on each side. When we look at this, the data that was collected here is called discrete data because it's countable data. That's what we did. We counted the frequency of how often a piece went from 114 to up to 115. We counted that there was 1 and we put it there, 1 here, 2, and so on. So when you talk about frequency and countable data, that's called discrete data. Well, what if we were interested in just a portion of this? We only wanted to know 114.25 or something like that. Well, what you do is you transform this data into continuous data, which means continuous means it can take on any value. And how we do that is we create something called the density curve. And all we do is really just smooth out our histogram. I'm going to attempt to do this. It's not easy. And let's say down here, 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 and it goes on in that direction. And then over this direction. Ooh, that looks pretty good. That's what it should look like. That's what the other side should look like too. And it continues on. And in a density curve, in this particular one, the area underneath here is going to be 1. So if we wanted to find the area from here, this part down, we can do it just with some simple geometric probability. And same thing here. If there's 1 here, and I'm not sure how many there are, I didn't count them up, but say there were 30, well, you'd have a 1 out of 30 chance of being in this little area. But if I wanted to go even further, what I did was, this allows me to take any value I want and find the area from that part down or from there up and so on. And it really is the main part of what we're going to be doing from here on in using this density curve. I'm going to show you on the chalkboard, but I wanted to show you really here the difference between discrete data and continuous. I decided to take it outside and use my whiteboard because people were telling me how boring it is to just see the screen and things move. It's a beautiful day, so I'm outside, and we're going to talk about right now the density curves. And you'll see there's all sorts of shapes when we talk about a density curve. And our density curve, for our purpose, one we're going to spend the most time on, is going to be this one here. Now this distribution up here, that's what a density curve does, is it describes the distribution. This one is uniform, this one will be skewed right, this is going to be normal, symmetrical. You're going to hear that term a lot. They're going to say the normal distribution, they'll talk about the normal curve. We're going to talk about this drawing right here. The reason why is because so many things in life and reality follow this pattern that we use it quite often. Even if the distribution doesn't, there's a way that we'll be able to make it fit this distribution, and you'll see from that we'll be able to calculate a lot of probabilities. So you'll hear it called the bell curve, all sorts of different things. Well, what we're going to look at first is we're going to compare those two distributions I just had there. This one, the one I said that we consider the normal curve, the mean and median will be the same. They're going to be right here in the middle. So if the data is symmetrical, distribution symmetrical here, the mean and median will be the same. If it's skewed, if I have skewed data where it follows the tail down that way, well, my median will be here somewhere, but my mean follows the tail because these upper values will pull the mean towards it. The mean is known as the balancing point. If I were to make this thing solid and then be able to balance it, it would balance right here on the mean. You can try it. Go cut it, drawing, cut it out. It actually really works. I've seen it done. But we're more concerned about this one. And that's really what we're going to talk about now, is the normal distribution. Here we have the normal curve. Now I'm not stopping. I'm fighting through this thing no matter what, because I've done this a couple of times. And I'm going to tell you everything I know about the normal curve. So what we need to see is that the normal curve is symmetrical. And the mean is right in the middle. It's at the highest point. The mean and median are the same in the normal curve. If I took this half and flipped it over, it'd be exactly the same. It's symmetrical. It gets closer and closer to the x-axis, but we'll never touch it. And the area under this curve is going to equal 1. All right, now, not only will it equal 1, but I can tell you that the distribution has certain numbers every single time. All right, so from away from the mean, if I were to travel one standard deviation in the positive direction, 1, 2, 3, and then 1, 2, 3 in the negative, I will know for a fact that one standard deviation away in this direction and this direction, 34% on each side, which means 68% of my data is contained within one standard deviation away from the mean. So if my mean was 100 and I were to say this is 110, this would be 90. So between 90 and 110, 68% of my data falls. 2 standard deviations away out to here, this is 13.5, this is 13.5. That's 95% of my data will fall within 2 standard deviations. Here, this is 2.35%. This is 2.35%. From here to here, 3 standard deviations away, 99.7% of my data fall within 3 standard deviations. Out here we have 0.15 and 0.15 in the tails. That'll give you your 100%. So here in this drawing, what you need to know, it's called the empirical rule, or you hear it called as the 68, 95, 99.7 rule for obvious reasons. It's easy to remember. You have to know these numbers. All right, we're going to be using them from here on in. What this allows us to do, and you'll see later on as we use this, I'll be able to find from any point on this curve, I'll be able to find the percent that scored from here down or here up, and I can do that because I know the area is 1, and I'm going to do some geometric probability. If the whole area is 1, and then, well then, what percentage is from here down? Well, there's 2.35 and 0.15. 2.5% of the data goes from here down. So again, I was saying if this was 100, my standard deviation was 10. This got me down to 90, 80, 70. So at 80 here, from 80 down, that's 2.5% of the data. So if you scored an 80, let's say this was a test, you scored better than 2.5% of the people that took the test. And we'll be doing a lot of this going forward. That sun's starting to come in, so let me click out of here.